Now, before we move off of type 1, we're going to talk about something that is sort of treated like a type 1 metal, even though technically speaking, it's a nonmetal. And that is hydrogen. So hydrogen has a lot of unusual sort of characteristics. And let me just kind of get rid of some of this up here so we can talk about it. So when we have hydrogen in the beginning, so for example, if we had something like HCl, we actually would think of this, even though it's technically two nonmetals, and even though technically, as we just drew it, it is sharing electrons and covalently bonded. It is oftentimes, in terms of naming, thought of as being more like a type 1 ionic compound. And what I mean by that is the hydrogen here is thought of as being H plus, and the Cl is Cl minus, and is thought of as being really more ionic. And that's really because that is the forerunner to hydrochloric acid, which when it does go for a swim to become hydrochloric acid, it becomes ions. So that's why people sort of think of it in that sense. So when we do have hydrogen in front, we just simply use the whole name like a type 1 and just call it hydrogen. And this would be chloride, which would be like the hydrogen chloride gas. Even if you had two hydrogens in front and it's not an acid, say it's something like a gas in each of these, this would be two H pluses and one sulfur that's -2. And that's why there's a 2 on the bottom there next to the hydrogen. This would also be called hydrogen sulfide, which maybe you'll smell a little bit of it when you go to 1B. Not pleasant at all. And this is hydrogen sulfide gas, not good for you either, so you shouldn't really smell too much of it. It's hydrogen sulfide. So hydrogen, even though both of those things are really covalently bonded together, sharing of electrons, in terms of naming, they're really thought more of like an ionic compound, and it's more so because they typically will become acids and they will become ions at that point. So that's how we sort of treat hydrogen that is in front. That's sort of positive. Any questions on that there? All right, then that means that if we did type 1, there must be type 2. So let's talk about type 2 and the major difference here. So type 2 is still ionic, which means it is still a metal and a nonmetal together. And still, it is the metal that is the most important thing here. And in this case, we're going to have a metal that has a variable positive charge. So these are our transition metals, obviously, except for zinc, cadmium, and silver, are again just to the right where lead, tin, and those guys are located. The difference between type 1 and type 2 is simply the metal can make a different positive charge. So when you name things, you actually need to tell people what charge you're talking about in this situation. So we actually name this very similar to how we do type 1. And I'm going to kind of get rid of this so I can write a little bit higher here. We actually will use the whole name of the metal, just like we do in type 1. We will actually do the nonmetal with the IDE, just like we do in type 1. So we'll do our nonmetal with the IDE. The difference is in between those two, we put a Roman numeral. Bless you. And the Roman numeral is the positive charge on the metal. Like if you took one metal out, what the positive charge is. It is not what most people confuse it to be how many metals you have. It's not how many metals you have. It is if you took one of those positively charged guys out, what the charge is. So the Roman numeral is the positive charge on the metal. Again, not the total positive charge, just one individual positive charge of what it is. So if we look at the example that we had there, the approach that you should take in this case is the exact same approach that we did previously. We're going to identify what we're dealing with. Iron is a metal. Cl is a nonmetal. So that tells me it's ionic. Fe, which is the metal, is the most important thing. If I look on the periodic table, dead center of the transition metal region, lucky number 20 something, 6. Lucky number 26, I think, is iron, which tells you it has a variable charge and that this is a type 2. So what that means is you need to take perhaps an extra step to figure out what the charge is on the metal. The good news is you will always know the charge on whatever it's attached to. So whatever that metal is attached to, you will know what the charge is. So if we take this, for example, all right, I know I need to figure out what my charge is on my iron, but I do see Cl there, and Cl is group number 7 on the periodic table. And that means that it should have a -1 charge. But there's not just one Cl there, there are 2, which means I actually have that happening. That's going to give me a -2 overall, which means my one iron must have what type of charge to balance it out? +2. Now I have everything I need to name this. I'm going to use the whole name of the metal, which will be iron. I'm going to lay myself up here a Roman numeral of 2 because that is the charge on the metal. And just like in type 1, it does not matter how many of those nonmetals you have, it is still just going to be called chloride. So this would be iron Roman numeral 2 chloride. First off, any questions on that? The reason we need to use the Roman numeral is if I had FeCl3, in this case, I would have an iron, I'm maybe not sure. I still have a chloride, but now I have not 2, but I have 3, which means I have a -3 overall. And in this case, the iron actually has a +3 to balance it out, right? And we need to tell people in this particular case, we're talking about iron with a Roman numeral of 3 or a charge of 3, and this would still be chloride. So we use the Roman numeral with type 2 metals to tell people what the positive charge is. And again, that is what the Roman numeral means. You take one of the positive charges out, and that is what you should have there. The rest is pretty much just like the other one. Yeah. Question on that there. So if I had something like maybe, that's pretty much what we just talked about. This, what should this name be? PB is lead, by the way. Take a moment and write the correct name for this guy. Got it. So PB is lead, which is a metal. Oxygen there is a nonmetal. So we know this is ionic. The lead is not a transition metal, but it's one of those ones to the right that does fall under type 2. It can have a variable charge. So we do need to figure out the charge here. So we do have one lead. We do know oxygen is group 6, which means it should have a -2 charge. And there are 2 of them. So if my math is correct here, that is -4. That means the lead here is actually carrying a +4 charge. And the proper name here would be lead Roman numeral 4 oxide. This would not be lead 2 oxide, which a lot of people will get because they just blindly move the 2 to the top. And so this is again an example of, if you've ever seen that or be taught that, you will get the wrong charge on both of those if you move those guys to the opposite side. Any questions on that one there? It would be not correct in this case. So you should not use, just like in type 1 in an ionic compound, type 2 is an ionic compound, you should not use prefixes. No. Other names for this, there are a older way of naming these type 2 compounds. We're not going to really use the older name here in this class. We will strictly use Roman numerals for type 2, but sometimes people will still use it, especially for iron and copper is very common. So in the older way of naming, use kind of the root of the historical type name, and the one that has the larger charge would end in ic. The one that had the smaller positive charge would end in us. So iron 3 would be ferric, and iron 2 would be ferrous. Same thing with copper, cupric, and cuprous is sometimes used still, but we will not use those names. But that's sort of the reasoning. What it is, ic is the higher positive charge, OS is the smaller positive charge. So again, we'll strictly use that. Here's a table of some of that and some of the older names. We're not going to worry too much about it, but you can see a lot of it is sort of really where they get some of the symbols from, by the way, for some of these things. The one thing I did want to mention is mercury, which is an oddity. This is mercury plus 2, 2. That is mercury plus 2. The first one, oddly, with all the 2s, is mercury 1. Yeah, so that has mercury 1 there. The one with only 1 2 is mercury 2. And that is because mercury 1 comes as a dimer, which means there's 2 mercury 1s stuck together, which is why they each have a +1 charge, which is where the +2 charge comes, and there is 1 and 2 of them, which is where the bottom 2 comes from. So the one with more 2s is actually mercury 1, and the one with less 2s is actually mercury 2. The way that you're able to recognize that is the bottom 2 still hangs around when you see it in a formula. So for example, if I had this Hg2Cl2 and HgCl2, top one is mercury 1 chloride, and you would need the Roman numeral. Again, that extra 2 is hanging out there. The bottom one is mercury 2 chloride, no 2 on the bottom. So that extra 2 kind of hangs out there, and that's how you kind of know it's the mercury 1 sort of ion. Any questions on that there? All right, so we kind of went through this. Same rules apply for our type 2. The only really additional thing we're doing is adding that Roman numeral to indicate the positive charge on the metal. And like I said before, you will always know what is attached to it. So just like last time, let's do some names on the guys here on the left. And again, I'll write it up towards the top in case it's hard to see. And I'll give you some names that you could write formulas for. So why don't you write the formulas for, let's do iron 3 oxide. Let's do copper 1 sulfide. And let's do chromium 4. Okay, let's take a look, see how you're doing. So again, we're going to identify what we're dealing with. CO here is a metal, CO is a non-metal. So once again, that tells us it's ionic. Always when that metal's involved, that's where you want to be looking. And that cobalt, again, right next to iron there on the periodic table. It's a transition metal, which tells us it has a variable charge. So that's a type 2 compound. So we want to, again, sort of figure out our charge on our cobalt. We do know that Cl is -1 from being from group 7, and there are 3 of them. That means to balance it out, our cobalt would have to have a +3 charge to do so. That means that this name here would be, I'm going to go right here underneath, cobalt Roman numeral 3 because of the charge. And again, doesn't matter how many we have, will be chloride in this case. Yeah. Any questions on that one there? Looking at the next one, Cu is not carbon, copper is copper, which is a metal, I think. I is iodine, which is a non-metal. So once again, that tells you it's ionic. We're going to look at our metal as our important guy there, and that's going to be a transition metal there, number 29. And that means we have a variable charge. We do know that I is group 7, has a -1 charge. So clearly to balance that out, we actually have a +1 charge on our copper. And this would be whole name of our metal, copper, Roman numeral 1 because of the charge, and iodide, ID. Any question on those two? Lastly, we have tin, which is a metal, and Br, which is a non-metal. tin again is a little bit to the right of the transition metal, but in that area where they still have a variable positive charge. So we got a tin, I'm not sure, but we do have Br, which is group 7, which means it should have a -1, and there are 4 of them, right? So we got a little bit of this happening. That gives me a -4 overall, means my tin should carry a +4, and this should be tin Roman numeral 4 because of the charge, and bromide. Any questions on any of those names? Yeah. All right. So working backwards from the name to the formula. Get rid of my cobalt there that I wrote. The nice thing about the name is when I see iron Roman numeral 3, I know the iron has what type of charge? +3. That is what it means. I don't have to figure anything out. It actually told me what the charge is. Oxide is oxygen, which is group 6, has a -2 charge. So when I put those together, common number there is 6, right? And to get iron to 6, I would need 2 of them. So I would need like 2 of these guys. To get oxygen to 6, I would need a grand total of 3 of them. And we should end up with something that looks like this. Yeah. Looking over here to copper Roman numeral 1, that tells me my copper is carrying a +1 charge. Sulfide is sulfur from the periodic table, which is group 6, has a -2 charge. In this case, I need more of the copper, grand total of 2 of them, which means I should have 2 coppers, right? That's where the number goes to, and 1 sulfur in this case, right? Or something that looks like a 5. There we go, make that more of an S. Any questions on that one there? Lastly, chromium Roman numeral 4 means my chromium has a +4 charge. Bromine, which is group 7, has a -1 charge. Once again, when we put this together, we're definitely going to need some more of the Br minuses. Grand total of 4 of them, which means I have CrBr4 in this case. Question on type 2, names or formulas. So exactly like type 1, except the additional thing, you need to figure out the charge and put the Roman numeral in there. There has been no prefixes, right, with Roman numerals. And if you find yourself like Roman numeraling and prefixing, just make an X for yourself as well, because it's probably going to be wrong. Yeah. So there's only one little spot where that might occur, but it definitely is not when any of these situations. So you should never really have a Roman numeral and a prefix kind of rolling together when you're naming. Any questions on any of those 2 types? All right, then let's talk about, this is just a summary here of what we just talked about. Again, group 1, 2, 3, zinc, cadmium, silver, no Roman numerals needed. Transition metals, and just to the right, do need Roman numerals, as we've been talking about. So let's take a look at a few more here. HGO would be what? Do I need a Roman numeral or not? Hg is mercury, right? That's a metal. Oxygen is a non-metal. Mercury is found in the transition metal, which means it does need a Roman numeral, right? And oxygen here is a -2. That means the mercury here should be a +2. And is this mercury 1 or 2? This is mercury 2. And this is mercury 2 oxide because there's not an extra 2 down there, right? So there's no extra 2 on the bottom. That's how we know that it is mercury 2. How about MgBr? Do we need a Roman numeral? No, because Mg is a fixed metal, type 1, which means we could just go whole name, which is magnesium. And bromine becomes bromide, right? Li2O, does it need a Roman numeral? No. Li is group 1, which means it has a +1 charge always. type 1, which means we could go right into the name of lithium oxide, right? Bottom guy there, just in case it's too low to see, is CrF2. Do I need a Roman numeral on this guy? I do. Chromium is a type 2 metal, transition metal. So we do have F, which is group 7, and there's 2 of them. That means in this case, my chromium is carrying a +2 charge. And this would be chromium Roman numeral 2 because of the charge, and fluoride, right? So chromium Roman numeral 2 fluoride. Any questions on any of those there? All right, so little decision tree in case you need help with the decision. We sort of been talking about it there. Well, we've been talking about don't use prefixes, don't use prefixes. Here's where we use prefixes. So this is where you should use prefixes when you name these things. And these are type 3 binary compounds. Binary just means there's 2 elements. But type 3 means it is 2 nonmetals together. And 2 nonmetals together means we're going to be sharing electrons. And this is really the place where we actually do use prefixes. We're going to have 2 nonmetals together. And we will use our prefixes like mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6. There's a table coming up, I think, that has these. Hepta is 7, octa is 8, a little nona maybe, I don't know, 9, perhaps some deca, maybe some 10. And these are the prefixes that we use. So here's how we do it. You'll have 2 elements, 2 nonmetals together, and you know that makes it a type 3 compound. And we will use the prefix if needed and the whole name of the first element. We will then use the prefix, and the second element gets the normal nonmetal treatment of IDE at the end. So we kind of prefix them and then IDE at the end. These are probably the easiest ones to do and probably the ones people screw up the most on because they want to do all kinds of weird things that they don't need to do. So try not to do that, by the way. There are a couple of rules that we follow when we're doing this. The first major rule is we do not use mono on the first name. So we do not use mono on the first name, but it is okay on the second name. So you could do it on the second name, but not the first name. In addition, because the prefixes end in vowels and the first letter of some of the elements are also vowels, what happens is sometimes you actually get 2 vowels that back up to each other. The 2 common problems are an O and an O, and like an A and an O. And typically we would get rid of the prefix off of the vowel off of the prefix part of the name. So an example of that would be something like this: CO, capital C, capital O. That's carbon and oxygen. They are both nonmetals, which means it's a type 3 compound. You don't have to worry about charges. You don't have to worry about balancing things. You frankly just need to count how many of each you have and pick the right prefix. So carbon, I only have 1, which means the prefix is mono, right? Do I use mono on the first name? I don't. So we're going to drop the mono and just use the whole name of the element. So that would be carbon. There's only 1 oxygen. Prefix is mono. Can I use mono on the second name? I can, so that's okay. So if you write mono, and then the oxygen becomes oxide, and you end up with carbon monoxide. They do not sell, right, carbon monoxide detectors. They sell carbon monoxide detectors, yes. And that is because, I don't know why that's because, but it is because we should get rid of that first O, and this really should be called carbon monoxide, with just the one O that's present. So we would get rid of that O off of the prefix and squeeze it together, and it then should be called carbon monoxide. Yeah. Any questions on that? So first element first in the name, second, guess the IDE. And if you have a name, same way, the first name, part of the name is the first guy in the formula. Second part is the second guy in the formula. So here's again some of those rules. And the prefix, again, mono not used, but okay on the second name. Oddly, two I's in a row are okay, but really it's the OO and the AO sort of combination that you have to get rid of some of those. Here's a little table of those prefixes and what we just talked about. And here's our considerations. Again, tetraoxide, we would drop the A, and it would just be tetroxide, no A there. And again, there's our mono that we would drop as well. And of course, water would be H2O still, not dihydrogen monoxide, or any of the favorite things I read on exams when I put water up there and all the funky names that people think get to put. Ammonia, again, is ammonia, not nitrogen trihydride either, so you should call it ammonia. And I think we added our methane to that list earlier. So methane as well is what you should call that. All right, so why don't we try a couple of these, and when we give you some names, a little dinitrogen, I don't know, pentoxide. Let's do a little sulfur hexafluoride. And let's do a made up thing of trioxygen. Maybe it exists somewhere. Who knows? Trioxygen, I don't know. Hexabromide, I don't think so, but we'll go with it. All right. So I give some names there on the left and give some formulas on the right there. Again, I'll write a little higher in case you need here. I2O7, CO2, and ECl3. Fastest ones did you do? But again, sometimes people really kind of mess up on these because they want to do weird things. So you still want to approach it the same way. What are we dealing with? So we'll take the first one here on the left. We have iodine, which is a nonmetal. We have oxygen, which is a nonmetal. So right off the bat, that should tell you it's a type 3, and that is prefix territory. That's a nice thing as well, because I don't have to worry about balancing charges or anything like that. I simply just need to pick the right prefix that goes with how much I have. So I look at the I and I see a 2, which means the prefix there is going to be di. Again, the first element, we use the whole name of it. So this would be diiodine. I look at the second element, that's a 7. So the prefix is hepta. And oxygen there will now be IDE at the end because it's the second element. And this will be a little hept oxide. Here I am going to drop the A off of the prefix so I don't get the A and the O combination happening. Any questions on that one there? Same thing for the next one. I'm going to look at it and go, C is carbon nonmetal, O is oxygen nonmetal, type 3 prefix, ready to roll. One carbon prefix is mono, but I know I should not use that on the first name. So we're just going to use the whole name here, and that would be carbon. There are 2, so the prefix for that is di. And again, the second element gets the IDE at the end of it. So this would be carbon dioxide. Yeah. Any question on those 2? Lastly, here I see P, which is a nonmetal, Cl, which is a nonmetal. So type 3. We only have one phosphorus, so we are, again, not going to use mono on the first name. So this would be the whole name, phosphorus or something. 3 prefix is tri. Second guy gets the IDE, so this will then become trichloride. Yeah. Any questions on any of those names there? No. So this is where we use prefixes. Again, nowhere else. The easiest of any naming you'll ever do is this one right coming up right here. This is probably the easiest of it all. I see tri, I see hexa. That makes me think type 3. I don't have to worry about anything other than write what it says. So tri is 3, oxygen is O. That's an O and a 3. Hexa is 6, bromine is Br. That's a Br and a 6, whatever that might be. Would be the formula there in that particular case. Again, I see di, which is a prefix, penta, which is a prefix, so could roll right into the formula. Nitrogen is N, di means 2, penta is 5, oxygen means O. So there it is, N2O5. Lastly, on the last one, I see sulfur, no prefix, but I do see hexa, which is a prefix, and I know the only place prefixes should be used is type 3, and they're both nonmetals as well, right? So I know that's going to be type 3. So sulfur with no prefix means there's only one, because that's our mono we're not using, right? And hexa is 6, and Cl is chloride. So a little bit of that action, yeah? Any questions on that there? All right, so everybody has its place of where it goes. Prefixes only for type 3 should only be used in non-metal action happening there. Roman numerals should only be used in a metal, non-metal situation where the metal is a transition metal or just to the right. None of the above in a type 1 situation, no Roman numerals, no prefixes, just the whole name and the IDE for the metal non. All right, so as we just saw there, type 1, type 2 ionic. So basically no Roman numerals, right? Type 2 needs Roman numerals, and type 3 needs prefixes, right? So again, each of these things has their own special thing of naming, basically. All right, little decision tree you can take a look at there. All right, the next thing we're going to talk about is polyatomic ions, and polyatomic ions are really groups of nonmetals together, and they actually are sharing electrons and covalently bonded, but because of how they are sharing electrons and who they're sharing electrons with, they actually end up having an overall sort of charge. And that means that if we take a look at an example like NH4NO3, we actually have, in this particular case, 2 different polyatomic ions. If you break it up right about there, we have this guy right here, which is NH4 plus. That 1 nitrogen and 4 hydrogen stays together as a whole unit and has an overall charge of +1. This guy right here is 1 nitrogen and 3 oxygens with a -1 charge. Once again, that nitrogen, 3 oxygens stay together as a whole unit and has a -1 charge. This is essentially an ionic compound, which is why we have a +1 and -1, which is why when we look at the formula, we just need one of each of those polyatomic ions. We actually drew both of these when we did Lewis structures, right? So if you remember, this is NH4 plus. These guys are all sharing electrons with an overall charge of +1. And this is nitrate, our double bonded guy here. With an overall charge here of -1. So again, -1 and +1. This is why these guys will never break apart into the individual elements, because they're sharing electrons. So they're bonded together. That's also why they move around as a unit. So you want to keep that in mind as you're doing it. These guys have special names and also special formulas that go with it. So for example, this guy here is what is known as the ammonium ion. not to be confused with what we just saw, which is NH3 that has no charge, which is ammonia. So ammonia, NH3, no charge. Ammonium, NH4 with a +1 charge. So they are different, those things. NO3 minus is what is known as the nitrate ion. The good news about polyatomic ions is this: you just use the name. It doesn't matter how many of them you have. You pretty much just use the actual name of the polyatomic ion when you go to name it. So that is what we would name this guy. First guy is ammonium. And second guy is nitrate. So this would be ammonium nitrate. We just use pretty much the whole name of the polyatomic ion. And again, no difference if there's one of them or 30 of them. We just use basically the whole name of it in the particular formula. Question on that there. Now, for the most part, most polyatomic ions are negatively charged. There's a few positive ones like this one. Hydronium ion is also positive, but the vast majority of polyatomic ions are actually negatively charged. So what usually happens when we have a polyatomic ion is usually will be hooked up with a metal. So a lot of times you will see a metal and a polyatomic ion together, as the polyatomic ion being negative and the metal being positive. So what happens in a lot of cases when we have a polyatomic ion and definitely a metal, and as we talked about with type 1 and type 2, whenever that metal is involved, it is really the important thing in terms of how you name it. So a lot of times we will fall back to our type 1, our type 2 naming when we're dealing with a polyatomic ion, because again, that metal sort of determines how you name it. So for example, here, if we were to look at, let's say here we had FeNO3 2, for example. Here we would look at it and go, that's a metal, and that is a polyatomic ion. Once again, because the metal's involved here, it is the one that's most important, and that is iron, which is a transition metal, which should tell us it is a type 2 situation that's happening here. So we do need a Roman numeral when we go to name this. We would do the same approach. We know we have one iron, and we have nitrate, which has a -1 charge, and there are two of them, which means overall -1 is -2. So just like before, to balance it out here, our iron in this particular case would be +2 to balance it out. And we do have to include that in the name, just like we would with a type 2 metal. And this would be iron, Roman numeral 2, once again for the charge on the metal. And again, even though there are two of the polyatomic ions, it has no effect on the name, so we would just call it nitrate at the end, and this would be nitrate. Questions on that there? We also see in the formula that I actually put parentheses around the polyatomic ion, and you should always do that when you have more than one polyatomic ion and you're writing a formula for it. You do need to put parentheses and how many there are on the bottom right. That is because if I just wrote it like this, that would imply I have what? About 32 oxygens, which is clearly not the case here. If we look over here, I only got about 6 oxygens that's actually happening. So whenever you have more than one polyatomic ion, you do need to put parentheses around it and the number on the bottom as a subscript as to how many you have. Again, will not have an effect on the name, but you do need to do that when you write the formula. If you just have one polyatomic ion in a formula, you don't need to put the parentheses. So sometimes people parentheses up everything. So you don't need to put the parentheses if there's just one. Also, if I had something like this, this would be NaNO3. Na is sodium, which is a metal. NO3, as we've been seeing, is nitrate. And again, it is the metal here that determines. So sodium's a type 1 metal, which has a fixed charge, which means we do not need a Roman numeral, and this would be known as sodium nitrate. It is made up of a sodium ion and a nitrate ion, -1 + 1 = 0. So 99 times out of 100, probably you will find a polyatomic ion pretty much hooked up with a metal. You could fall back on pretty much the type 1, type 2 rules and just use the whole name for the polyatomic ion. Any questions on that there? So here's a list. Here's another list of some polyatomic ions. They're up on Canvas as well separately, I think, as PDFs in the exam review if you want a kind of a bigger version of it. But these are the polyatomic ions, and it's a good way. You do have to unfortunately memorize these. They want you to know these. So you need to know the names. You need to know the charges that go with it so you can balance out everything. But there is sort of a way that you can kind of look at these and sort of maybe figure out and learn them. So there are patterns when we look at polyatomic ions. So for example, if we had our NO3 minus that we just saw there, which is nitrate, AT, we have NO2 minus, that is nitrite. We have something like SO4 2 minus, that is sulfate, and SO3 2 minus is sulfite. So you can kind of group these things up as like groups of 2, and there's also groups of 4 as well. But with a group of 2, with the most oxygen will end in 8, and the one with the least number of oxygen will end in ite, and that's what we see here. They all have the same charge in this case, right? NO3 minus, NO2 minus. They both have exactly the same charge. The only difference is the number of oxygens. The one with more oxygens in this group ends in 8. The one with least oxygens ends in ite. Here, SO4 2 minus and SO3 2 minus. They both have the same charge. The one with more oxygens ends in 8, and the one with least oxygens ends in ite. So usually the one that ends in 8, more oxygens, and the one that ends in ite, less oxygens. Now, there are ways that you could help yourself sort of remember these. So sometimes people will, for example, remember all the ites and their formulas and just know that if I need an 8, just add an oxygen, everything else is the same. Or you could do the opposite, remember the 8s, and know if you need an ite, just drop off an oxygen from it. So that's a good way to sort of remember it and figure it out, is just maybe learn one of those guys, the 8s or the ites, and know that to adjust it, either add an oxygen or drop off an oxygen from its name. So what do I mean by that? For example, this guy is phosphate. And if I wanted phosphite, it should have one less oxygen. Everything else would be the same. So it would just drop off basically one oxygen and will be the phosphite. So if I had this guy, which is carbonate, and I wanted carbonite, how many oxygens should it have? 2, it'd be CO2 2 minus. So again, that is a way you could kind of adjust it if you just maybe learn one of them and know go up or down based off of that. Any questions on that there? There's also groups of 4 that are related to each other, and the most common group of 4, maybe I'll do it over here ish maybe, is really yeah, another table in case you missed it. I'll do this one here. This group of 4 is related to each other: ClO4 minus, ClO3 minus, ClO2 minus, ClO minus. So all these are related to each other. They're all basically have a -1 charge. The only difference is the number of oxygens in each of them. So all these guys, all -1s. So in a group of 4, what you could do is the same thing. You kind of break it up by 2s. So if we go to the right-hand side, those are guys that have the least number of oxygens in that group of 4, and they should end in ite, right? Because the least number of oxygens should end in ite. So this would be chlorite. This guy here would be chlorite. You clearly cannot have the same name for 2 different things. So when you have a group of 4, the one that has the least number of oxygens in that group of 4 in addition to ending in "ite," we'll start with hypo. So the guy at the end is what is known as hypochlorite. We could do the same thing for the guys on the left. They have the largest number of oxygens in this group of 4, which means they all should end in "ate." So this would be chlorate. And this guy would be chlorate. Again, we can't have 2 names for the same thing, or same name for 2 different things. So in this case, in a group of 4 that has the most oxygens in a kind of a run of 4, we'll actually start with per in front of it. So this is what is known as perchlorate. So there are groups of 4 that are related to each other. You can kind of break them up the same way. Ite and H should be the endings. And again, the additional for those guys at the ends, per for the guy with the most oxygens, and hypo for the least. The guy right there is Cl, which is a halogen. You could replace really that halogen with any halogen. It's named the same way. If you had to take a guess, what would BrO3 minus be? ClO3 minus is chlorate. So BrO3 minus should be bromate. Yeah. BrO2 minus should be bromite. Yeah. So again, you could swap it out for any of those halogens. IO3 minus would be iodate. Yeah. So again, this is how you could kind of pretty straightforwardly, hopefully, figure out some of these polyatomic ions. So there are groups of 2s, groups of 4, they're related to each other. Any questions on that there? A couple other things, if we look at the table that we will see. Erase some of my scribbling here. There are certain ones where we add, for example, hydrogen in front of it or H plus in front of it. So we looked at our carbonate, which is CO3 2 minus. That is carbonate. And if I put an H plus in front of it, that gives me HCO3 minus. The charge changes because it's +1 -2 and ends up as a -1 charge. I essentially put hydrogen in front of it. So this is what is known as hydrogen carbonate. And hydrogen carbonate, or hydrogen, is also still historically used and very commonly used as bi instead of hydrogen. And this is what is known as bicarbonate. Also happens with sulfate and phosphate. That's hydrogen phosphate. We have bisulfate as well that happens with. So you could have something like, this is SO4 2 minus, which is sulfate. Putting that H plus in front of it gives you HS, too many H's, HSO4 minus, which is bisulfate or hydrogen sulfate. So that's another very common thing that you'll see on a polyatomic ion table. For example, you could also have dihydrogen phosphate, which has 2 hydrogens here as well. So you'll have some of these other things that can happen on our polyatomic ion table. Although a vast majority of them do end in either ite or ate, there are some polyatomic ions that do end in IDE as well. So hydroxide, OH minus, ends in IDE. Cyanide as well ends in IDE. Azide as well ends in IDE. But a vast majority of them will be, again, probably ATE or ITE in terms of it. Any questions on that there? All right, so let's try a few here just to make sure. All right, I'll leave this table up here. So we'll do, what is the name of the following here? Let's do CuOH2. Let's do NiSO4. Let's do Na 2CO3. And then why don't you also write the name for iron 3 cyanide. Why don't you do sodium chlorate? And why don't you do ammonium sulfide? All right, so names for those guys that are formulas and formulas for the guys that have the names there. And we want to kind of identify what we got going on. We'll start up here. That is sodium, which is a metal. That is CO3, which is carbonate. So that is basically our sodium ion and our carbonate ion here. And again, because the metal's involved, that's really most important. And that metal is a type 1 metal, which means we do not need a Roman numeral. So there's really nothing to figure out at this point to name it. We'll use the whole name of the metal, which would be sodium. And we would use the whole name of the polyatomic ion, which would be carbonate. Any questions on that? Just like with type 1, it doesn't matter. There's 2 sodiums, has no effect on the naming. Any questions on that one there? Taking a look at the one there here in the middle, that is copper, which is a metal. That is hydroxide, which is a non-metal. In this case, that copper is a type 2 metal, which means we do need to figure out the charge on it. We do know that hydroxide from the table here is OH minus, and there are 2 of them, which gives us a -2 overall sort of charge. We have only 1 copper in this case, so to balance it out, it needs to be +2 in this case, and that means it does need a Roman numeral here, and I'll just write it over here. That would be copper, Roman numeral 2, again for the charge that's on the copper, and even though there are 2 of the hydroxides, has no effect on the name, it would be hydroxide in this case. Any questions on that one there? Looking at the last one, that is Ni, which is nickel. Also a transition metal, which tells us it's a type 2 metal. SO4 is sulfate. So here again, we need to figure out the charge on the nickel. Our sulfate from our table is SO4 2-, which means it has a -2 charge. That means to balance it out in this case, our nickel has to carry a +2 charge, and we would again here need a Roman numeral. And for our Roman numeral there, it would be 2. And I'll just write it up here. This would be nickel, Roman numeral 2, and our sulfate. Any questions on any of those names there? Now going backwards here from the formula to the name, we're just going to basically put it together. I have iron 3, which I know is iron with a +3 charge because of that. Cyanide is right there, which is Cn-. So in this case, as an ionic compound, we want to get to 0. We basically need not one of these guys, but we do need 3 of those guys to balance out the charge. And that would get us our proper formula here of Fe. We do need to put parentheses because there's more than one of them, of these polyatomic ions, Cn and A3 on the bottom there. Any questions on that one there? Coming up the next one, which is sodium chlorate, it looks like I wrote. And sodium is group 1, which means it has a +1 charge. Chlorate's one of our group of 4 that are related to each other, which is actually ClO3-. We are ultimately putting a +1 and -1 together, which means we just need 1 of each. And that would give us, I'll put the formula over here, NaClO3. Once again here, because we only have 1 of the polyatomic ions, there really is no need for parentheses or anything like that in the formula. Any questions on those too? Yeah, so these are really polyatomic ions when they hook up with metals or just in general. They're really ionic compounds. So just like our ionic compounds we talked about with type 1, type 2, whenever we put that positive negative guy together, we want 0 overall charge. So there should be no charge in the formula when they come together, just like type 1, type 2, but they are made up of two, individual sort of ions and stuff like that. So other questions? Okay, lastly here we have ammonium sulfide. Ammonium is our few positive guy right there, NH4 plus, and sulfide is actually from the periodic table, group 6, which is -2 there. So we basically have NH4 plus and -2. In this case, to balance out the charge, we will need one more of those positive guys. And since that is actually a polyatomic ion, we again need the parentheses. So that's going to be NH4, 2, and S in this case there. Any questions on any of those polyatomic ions? All right, so the school would like you to know these, yes? So probably learn this table. You'll have pretty much all of the ones you probably will need, I assume, as you go through life in chemistry. Any questions on that there? Yeah. And again, obviously, they will not be provided for you. Yes. Okay. All right. There's a few more tables in case you missed it. All right. So we talked about these patterns, but again, just to reiterate, to look at these slides here. Again, in a group of 4, we're going to put per on the one that has the most oxygens. Going to start it with that, end with 8, and the one with the least oxygens, hypo as well. So again, you could adjust up or down just by learning one of them. So again, if that's sulfate, what happens if I wanted persulfate? How many oxygens should it have? Persulfate, so 8 means more oxygens, right? And per means that it should have actually one more than this guy, right? So that would be like SO5, 2 minus, right? If I wanted sulfite, ITE should have 1 less. If I wanted hyposulfite, it should be SO2, 2 minus. Yeah. So again, you could adjust up or down in that sort of group of 4. If you can go sort of the basic one of those and kind of adjust. Again, everything else stays the same with these guys. The charges stay the same. It's just really the number of oxygens that change as you kind of go up or down. Any questions on that there? All right. And again, as we saw there, we can swap out a halogen and it will be named the same way. And also when we add hydrogen, remember that when we do add the hydrogen, it's really the hydrogen ion. So that plus is important because it does adjust the charge. As we said, it went from carbonate to hydrogen carbonate. It is not just the H that we're adding, but that plus 1 and -2 gives us a -1 left over. So you got to adjust the charge as well when you add the H plus to it. All right. There you go. I'll just scroll through these since we kind of really covered all this as we went through it there. All right. The next thing that we're going to talk about is naming acids. And acids are substances that have the ability to produce H plus ions in solution. H plus ions are sometimes referred to as protons. And that is because, as we know, hydrogen has 1 proton, right? 1 electron and no neutrons. So when something becomes positively charged, it lost an electron, which means hydrogen is just left with a proton at this point. So that's why it's sometimes very commonly referred to as a proton in acid-base chemistry. Also, as we'll see when we get to the acid-base chapter, H plus and another polyatomic ion, H3O plus, which is known as the hydronium ion. Hydronium ion. Are basically the same. So they're used sort of interchangeable in acids. So especially when you're doing acid-base type of chemistry, you'll see H plus, H3O plus sort of used interchangeable. They basically both mean the acid part of the solution. But for our acids, H plus is really important. All acids can be thought of as really a ion and an ionic compound, and the cation for all acids, the positive ion for all acids, is H plus. So that is like basically your positive guy for all acids. Acids are really, again, as I said, they're something that can produce H plus in solution. And it basically means that when you have a solution, the amount of H plus you got floating around will determine, if it's acidic, basic, or neutral, really. And because of that, acids also, when you write the formulas, should typically have aqueous next to it. And aqueous means water environment, that's a solution. And so typically when you do write the formulas for your acid, you do want to put that little aqueous symbol next to it. Because, for example, if you had something like HCl that's aqueous, that is hydrochloric acid. You have like HCl that's like in the gas phase, that is called hydrogen chloride. So the aqueous part is really important for an acid. Basically, you could take the hydrogen chloride gas, bubble it through water, and now you have aqueous hydrochloric acid, basically, in that solution. So it's really important to make sure you always include that aqueous on your formulas for things that are acids. So let's talk about pretty much the rules for acids and naming them. And it really all comes down to pretty much, is there oxygen or is there not oxygen basically involved? And if there is oxygen versus no oxygen, we do name it differently. I'm just going to look for a clear page to do this, I think. We'll just kind of summarize it here, I think. So when we go about naming acids, it's all about that oxygen. So if the answer is no, there is no oxygen involved, the acid name starts with hydro, something ic acid. The middle part that's missing is the negative ion that's attached to the hydrogen. So again, hydrogen is always going to be the positive guy. The negative guy is what the missing part of it is. So again, here, if we had our HCl, as we just saw, there is no oxygen here. This is basically H plus and Cl minus. And this would be, again, our hydrochloric acid, again, based off of our negative guy here. HBr then should be bromic acid. Again, Br minus, H plus, yeah. How about H2S? That's an acid here. That should be what? Hydrosulfur, right? So hydrosulfuric acid, yeah. There are two hydrogens here because sulfur is a -2, and we would need 1 and 2 of those hydrogens to balance out the charge. So hydro, which people want to use on every acid name, is only for acids that do not have oxygen involved. So if there's no oxygen involved, it should start with hydro, so end with ic, and the middle part should be kind of the negative guy's name, sort of filling in this space there in the middle. Any questions on that one? HI would be what then? HI should be hydroiodic acid, yeah? So this would be hydroiodic acid. HCN would be, so is CN is cyanide, right? So this would be hydrocyanic acid, yeah? So that is what this would be, hydrocyanic acid. All right, so no oxygen, start with hydro, end with ic, kind of fill in the middle part with the negative guy. Now, if it does contain oxygen, it's a little bit different, and it will contain probably one of those polyatomic ions that we just saw on that list. So if you do have an acid that does have oxygen in it, and again here, maybe I'll clear out some of this side of this thing. We'll borrow it here. Okay, so if we have an acid and the answer is yes, there is oxygen, it will contain your polyatomic ion in it. And as we saw, they pretty much end in ate or ite, right? These are also sometimes referred to as oxyacids because they contain oxygen. So that's why they're referred to obviously as oxyacids. So starting with if it does contain oxygen and your polyatomic ion ends in ate, your acid name will be something ic acid. So if we take HNO3, NO3 is nitrate, which means this would become nitric acid. H2SO4. SO4 is sulfate, which means this should be called, what do you think it should be called? Sulfuric acid. Once again, there are two hydrogens here to balance out the charge on the sulfate, which is -2. So again, the top guy there, there's only one hydrogen because this guy is nitrate that has a -1 charge. So they all balance each other out. So you could think really as acids, it's like ionic compounds. You want to balance out the positive charge from the hydrogen with the negative charge to equal 0. Even though in reality, these are all basically sharing electrons, they're all sort of covalently bonded. In terms of naming, we kind of think again of it as more ionic because when it goes into solution, it's able to release that hydrogen as an ion and create an ion as a result of that. This guy right here, H3PO4, that is phosphate, which means this should be called phosphoric acid. Yeah. Let's have our IC. Any question on those there? Now, if it, I'm just gonna put a box this way, maybe. If it does contain oxygen and your polyatomic ion ends in ite, your acid will be something OUS acid. So HNO2, for example. NO2 is NO2 minus, which is nitrite. And that means that this acid should then be called nitrous acid. Yeah. Nitrous acid. H2SO3. SO3 is SO3 2 minus, which is sulfite, which means this should then become sulfurous acid. So this would be sulfurous acid. How about HClO? What would that one be called? And what would HClO4 be called? Here we want to see it has oxygen, so that's a polyatomic ion. That is ClO minus, which is hypochlorite. And you do keep the hypo in the name here, so this would be hypochlorous acid, as that's hypochlorite. This right here is ClO4 minus, which is perchlorate, and you would keep the per in it, and this is perchloric acid. So again, even on those polyatomic ions where they got the per or the hypo in it, you do keep that with the acid name, and again, just end it sort of differently. Any questions on that there? There is absolutely no hydro here with oxygen involved. So if there's oxygen, you should not use hydro. Hydro is specifically for guys that do not have oxygen. Any questions on how to name acids? All right, so that again is what we just went over there. So ic or us, if it does contain oxygen and a polyatomic ion, hydro if there is no oxygen involved, and ending with ic. There we go. So there's a table from your book, and again, there's all these guys do not have oxygen, so you can see they all start with hydro. They all end with ic, and again, the middle part is based on the negative ion that is present. So this would be H plus and F minus, H plus and Cl minus, and obviously, as you can see there, hydrosulfuric acid and hydrous ionic acid we did as well. These all have oxygen, which are oxyacids. They all contain polyatomic ions, which are the ones underlined here. That right there is acetate, and that is how we get acetic acid, which is basically like vinegar, as the name for that particular one as well. All right, so we kind of solved both of those. So HF has no oxygen, so that should be the hydrofluoric acid. And this one does have, again, our oxygen, and that was, as we saw earlier, nitrate, which means it should then become our nitric acid. Any questions on acids or how to name it? By the way, if you have the name, for example, if you had phosphoric acid and you're not really sure like how to go backwards, right? So you could use the name to your advantage. The first thing that you should know is an acid, which means the positive guy should be H plus. So that's automatically, you should know that. What I look here when I look at this part of the name is there is no hydro, right? Which means that this guy does contain oxygen. And because it does contain oxygen, I know that it's a polyatomic ion. And I know that my polyatomic ion will probably end in either 8 or ite. And I know that when I do it for the acid, this one particularly ended in ic, which means that the polyatomic ion should end in 8. Yeah, if you kind of go backwards. So frankly, if you just cross out the ic and put an 8, phosphorate, yeah, so now you know what polyatomic ion it is, and then you would now proceed basically just to put together like normal. So in this case, we would need our 3 hydrogens to give us our H3PO4. So if I had something like, we'll do our hydroiodic acid. We'll do our, let's do our carbonic acid. And let's do our let's do chlorous acid. All right, so write the formula for each of those 3 there as to what it should be. Okay, so let's take a look. So once again, these are all acids, and we know that for sure that the positive guy is going to be H plus in this case. When I look at this one, I see hydro, which tells me there is no oxygen involved. So I don't have to worry about a polyatomic ion and iodic there. It looks like iodine, and that is group 7. So we're just going to put that together to get us our H. And again, we do want to put the aqueous symbol next to it to indicate that it is an acid. When I look at carbonic acid, there is no hydro, which tells me it does contain oxygen. And that means that, again, the H plus is going to be the positive guy. This ends in ic, which means if I cross it out, my polyatomic ion ends in 8, and that's like carbonate. And I know hopefully at some point that that is CO3 2 minus. So again, we want to put it together to balance it out. So we're going to need one more hydrogen, and that will give us H2CO3. Any questions on that there? So again, you can kind of use the name to work backwards. Once again, here on the bottom, I see no hydro, which tells me that, again, it's a polyatomic ion, and it contains oxygen. I see chlorus, so OUS means that the polyatomic ion ends in ite, so that is chlorite. So I know that that is ClO2 minus. So now all I have to do is put it together properly, and that would be HClO2 and aqueous. Any questions on going from the acid name back to the formula? So that's a really good way to do it. Cross out the back part, put ite or 8 if it contains oxygen, and that will definitely tell you pretty much the name of the polyatomic ion, and you can get the correct formula. Any questions on that there? Okay, we will lay it up. That is